So let's now have a look how much different we can proceed if we've got a measure. So I will now introduce a different way. So it's just some very rough introduction to something which would be called measure theory, and we shall not go into any detail. It's beyond the scope. Well, maybe later I will add some paragraphs on that somewhere later in the book, but not now. It's not there. It's not your task to learn it, but just I would feel sad not to tell anything. So what we shall deal with is what the people usually called Lebesgue integration. And that's because the guy called Lebesgue just introduced this way, another way of integrating, and it's quite actually more straightforward than one would think, and it's a question why not to teach it this way, but still the Riemann integration is perhaps easier to get hold in, and it's so straightforwardly linked to the intuitive ideas, so therefore perhaps the people always prefer to go this way. But the Lebesgue integration goes as follows. So imagine this is the real line or any other space. That's the advantage, because we don't have to stick to real line, so we could just take any space X equipped with a measure, and measure would be just a reasonable function which is defined on some sigma algebras of subsets in X. This is a system of subsets which is closed with respect to intersections and unions, and well, I mean not only finite unions but also countable unions of sets, and the function should be then having the properties of measure which I pointed out in the last presentation. So it must be sigma additive, etc. And then what we can do is the following. So we can just imagine we've got a function like this, and we want to integrate it. So instead of doing what we did before, we just split the values into subintervals, right? And for each of them we simply get something like this. And you see, for each of the small intervals we get small bits here on the space X. So it can be any space, right? Rn, much bigger space. As soon as you have got a measure there, it will work, right? So we have got a measure mu on these guys, and so I know what is the value. Well, what is the size of this thing? So this would be something like AI, right? Altogether it's AI, and I know the measure of AI. And I take the lower value, so of the interval, as the representative. Well, so actually I drew it wrong. So there are two small things here instead of one big, right? So I take this lower value as the one approximating. So this will be something like yi. I should keep the colors. So yi times the set. So simply I take the approximation from below, and I take on how big domain it is, and this is the contribution of this small value, right? And of course what we have to assume is that the pre-images of all intervals, so we have got a real valued function, so this must be real, right? you have a real valued function, and with the property that the pre-images of every interval are measurable. So they've got the measure. So all the pre-images of intervals must belong to our sigma algebra of the sets which are measurable, and therefore we have got the value mu on them. And now what shall we do? So simply we first define the integral, how it works on these step functions. So it's always just having only the lower value levels. So that's the approximation of the genuine functions, and we shall work only with positive values. So that's the restriction we are enforced to accept. Why doesn't it work? I hate this. Right, so we simply have to work with functions fx is always bigger or equal to 0. We approximate them from below, and if we have got a function which is not of this kind, we simply split it into the positive part and the negative part, and then in the end of the way we subtract it. So this integration, it's always working that the integral over some, say, interval I will exist if and only if the integral of absolute value exists, right? So this is the definition of the integrability, because if this exists, then we can split the domain into two parts, those where f is positive and negative. The integral will again exist, and we simply subtract the values. So that's okay. So this is the abstract notion of integration, and you see that with if our measure on a real line was the Dirac delta measure in some point, then of course this approach to integration will give you the evaluation in that point, right? So that's it. So I think I will not go into further details here with the abstract integration. Maybe just one last notice, and this is the Lebesgue measure. Lebesgue. Well, actually, two remarks. Lebesgue. Measure on R. Unique. So sigma is the smallest algebra of subsets, includes all intervals, and this is the unique measure which has the property that mu of an integral IB, well, it doesn't depend whether it's open or closed, is b minus a, right? So that's one of the ways how to understand it. It's quite difficult to prove this and to construct the Lebesgue measure directly, explicitly. Much more complicated than the approach via the Riemann integration. But one can get to a real measure concept with the sigma additivity and everything. Well, the second promised comment is the so-called Ries well, I don't remember the name, how it's spelled, Ries, well, perhaps the other way around. Representation theorem, and this tells a very nice thing. So you can imagine you have any space X, and imagine that which is something like real line. So you have got topology there. You know what continuous is, right? So don't bother with the definitions and so on, but we know it for a real line and a complex plane. So and there will be a functional which will be, say, lambda will go from continuous functions continuous functions on X with compact support. So compact means that the subset is, if it's covered by any system of open sets, then there is always the finite subset already covering, and this goes into R, and it's a linear functional. We know what it is. So it's just a linear map. So the smooth of the space of continuous functions is a vector space. We know what linear means, and linear functional means that the values are in the scalars R. No problem. And then there is exactly one measure on X such that the integral of f d mu on X extends lambda. So it means that it will reproduce the same values as the linear functional, and it will work on all the measurable functions, right? Those where the pre-images of intervals are measurable. This is a very strong theorem, and for us it's absolutely splendid because simply the Riemann integral is such a guy, right? So we can take the Riemann integral for the lambda, and there will be exactly one measure on the real line which will reproduce the Riemann integration via this concept of the absolutely convergent intervals, right? So this is very nice, and this is the end of this part. So some general glimpses towards measure theory. If you are confused, was too complicated, too much, just forget. Maybe you will come back later.